Section 4.5 deals with the superposition principle. So to illustrate the superposition principle, let's look at an example. So let's suppose we have the differential equation y double prime plus 3y prime plus 5y equals some function of t. Now, we might have a series of differential equations that have a certain combination of second derivative, first derivative, and function, such as we have on the left side, but what it's equal to might be different values. So we might have that same linear combination, but instead of equaling f, another time it might equal g. So let's see what would happen to our solution if we have a combination of f and g on the left side. So how is adding those together going to affect our solution to our equation? So let's suppose that the solution, or a solution to the first equation, we call y1, and the solution to the second one we call y2. Then let's show that the solution to the new differential equation, which is on the right side, is the sum of the right sides of the previous two differential equations. Let's show that the solution of that is just going to be the first solution plus the second solution. If the right side comes from adding f and g, then let's suppose that the solution comes from adding y1 and y2. So how would we do that? Well, if y is y1 plus y2, then y prime would be the derivative of y1 plus the derivative of y2, and y double prime would be y1 double prime plus y2 double prime. So in our differential equation, we're going to replace y double prime with y1 double prime plus y2 double prime. And then we have 3 times the first derivative, which is y1 prime plus y2 prime, and 5 times the function, which is y1 plus y2. So we have a y1 double prime. We have 3 times y1 prime. We have 5 times y1. So that's the terms that include y1. And then we have a y2 double prime, a 3 y sub 2 prime, and a 5 y sub 2. Notice that y sub 1 double prime plus 3 y sub 1 prime plus 5 y sub 1, that should equal f of t. If y1 is the solution to this differential equation, then that means that when we take the first derivative and the second derivative of y1 and plug it in here, that equals f of t. So this is f of t. If y2 is a solution to this differential equation, then that means that when we take the first and second derivative and plug it in for y here, and plug this in for y, that linear combination makes g. And that's what we have on the right side. So yes, it is true that if we know the solution of this differential equation and the solution of this one, that if we combine the right sides by adding or subtracting them, then the overall solution will come from simply adding or subtracting the solutions to these two differential equations. We can also demonstrate that if we multiply one of these functions by a constant, for example, if we change the top differential equation, y double prime plus 3y prime plus 5y, if we change the left side to be, instead of just f of t, if we call it, let's say, some constant times f of t, that if the solution to this differential equation is y1, that if we change the right side by multiplying it by a constant, that changes the solution by multiplying it by that same constant. So let's demonstrate that this is a solution to this new differential equation. So if this is the solution, if y is k times y sub 1, then y prime, k is a constant, so leave it alone, times the derivative of y1 prime, or y1. The second derivative, again, k is a constant, and then take the derivative of y1 prime, and that would be y1 double prime. So if we replace the second derivative with k times y sub 1 double prime, the first derivative with k times y1 prime, and y with k times y1. Notice all three terms have a common factor of k, so we can take the k out. That leaves us y1 double prime, 3y1 prime, 5y1. Well, since y1 is a solution, to this differential equation, then when we plug the second derivative and the first derivative and y1 in to the left side, that equals f of t. So this is just f of t, which is what we said we would get on the right side. So the benefit of that is if we know, if we have several differential equations that mirror each other, and we know the solutions with various terms, various functions on the right, then if we have a linear combination, whether it be those functions themselves added together or multiples of those functions added together, then we can generate a solution for that added or subtracted, linearly combined right side. And that's what's known as the superposition principle. So this is the way it's written. If y1 is a solution to this differential equation, and y2 is the solution of this differential equation, then regardless of what k1 and k2 are, then this will be a solution to this new differential equation. So if we take k1 times the solution to the first one, k2 times the solution to the second one, add those together, that would be a solution to the new differential equation that has the same left side, but the right side is this constant times this function, this constant times that function. So there's some benefits of this. Let's look at one direct result. If we have some second order differential equation, let me just call this f of t. And the solution of that, let's call the solution of that y1 of t. And that's the particular solution. Then if we look at the solution to the homogeneous differential equation, then the solution to the homogeneous, notice the characteristic equation is r squared plus 3r minus 4 equals 0, which factors to r plus 4, r minus 1. So we get r is negative 4 and r equals 1. So the homogeneous solution is c1 e to the negative 4t plus c2 e to the 1t. So that's the homogeneous solution. If y1 of t is the particular solution, then we can say that the general solution is the sum of these. The sum of the homogeneous solution plus the particular solution. So real quickly, let's look to see why this is the case. So this is because of the superposition principle. So our differential equation, we could write the right side as 0 plus f of t. So y sub h, that's the solution when the left side equals to 0. Y sub 1, that's the solution when the right side equals f of t. So if we have the sum of the homogeneous plus the particular, then our overall solution will be the homogeneous solution plus the particular solution. So in this case, our solution would be our homogeneous. That's our homogeneous. Plus, we call our particular solution y1 of t because we don't know what the actual function is. So in a couple of sections ago, we looked at finding homogeneous solutions. In the previous section, we found out how to get particular solutions by the method of undetermined coefficients. So our actual solution is a sum of those two things. And again, that's because regardless of the function on the right side, it can be written as a sum of that function plus 0, which means that when we substitute the homogeneous solution in, if the homogeneous solution is added in, that's going to add up to 0. And then if we put the particular solution, when we put that in, that's going to add up to some function. And 0 plus that function will also be that same function. Hence, our general solution will be that linear combination. So let's work through, let's take a look at this one. They tell us that for this particular differential equation, with this right side, this is a particular solution. So we're asked to find the general solution. So our general solution, remember, that's going to be our homogeneous solution plus our particular solution. So the particular solution comes from solving the differential equation when we have this function on the right side. And that's going to be e to the x plus 4x squared. So our job is just to find the homogeneous solution, and then this solution that they give us plus that homogeneous will be our overall solution. So our homogeneous differential equation will be y double prime plus 15y prime plus 56y equals 0, making our auxiliary equation r squared plus 15r plus, I said 5, that should be a 56 there, plus 56y equals 0, which factors to r plus 7, r plus 8. So we get r equals -7, r equals -8, which makes our homogeneous solution C1 e to the -7t plus C2 e to the -8t. So our general solution will be that, the homogeneous solution, plus the solution that we were given when we have this function on the right. So the solution when we have that function on the right is e to the x plus 4x squared. So again, since the right side can be written as 0 plus that function, then the solution of this is the solution when we have a 0 on the right side plus the solution when we have that function on the right side. So this is what we got when we had a 0 on the right side. This is what we got when we had that function on the right side for our. So our overall solution is just the sum of those. Now this question asks us to determine whether we can use the superposition principle and the method of undetermined coefficients with this problem. So we take it piece by piece. So if we look at the first term, then for just the first term, we could use undetermined coefficients to find that. And if we look at the second term, we can use undetermined coefficients to find that, because if we have either sine or cosine, we can do that. If we have e to a power, we can handle that. And if we have a polynomial, we can handle that. But if we look at this last term, 1 over t, or t to the negative 1, that's not exponential, that's not a sine, cosine, and since our exponent of t is negative, that's also not polynomial. So the answer to this is no. We cannot use the superposition principle combined with undetermined coefficients to solve this particular differential equation. All right, so this one wants us to find the general solution. So let's begin by finding the homogeneous solution. So our auxiliary or characteristic equation is r double prime minus 1, r squared minus 1 equals 0, which factors to r minus 1, r plus 1, which means r is 1 and r is negative 1. So our homogeneous solution is c1 e to the 1t plus c2 e to the minus t. So that's our homogeneous solution. Now for our particular solution, we need to figure out what the formula that's going to be. So for this term, since that's a polynomial, then we need to take into consideration from t to the first power all the way down to a constant. So we could have a t to the first, and we could have no t's. So a constant with t to the first and no t's. So that's the format of our particular solution. So the first derivative of that would be a. The second derivative of that would be 0. So if we substitute that in, we get our second derivative is 0 minus our function at plus b. That's the left side. The right side is minus at plus 5. Now you might say, well, what about for this part? For this part of the solution, then we have just a constant, but that's encompassed in this. So if we distribute the negative on the left, then we get minus at minus b equals minus 18t plus 5. So the coefficient of t is negative 18. So negative a is negative 18, which makes a 18. The constant, negative b, equals positive 5, which makes b negative 5. So that means our particular solution is a 18, t plus b, b is negative 5. So that's our particular solution. That just came from setting the coefficients of t equal to each other and the constants equal to each other. So then our general solution is just a linear combination of the homogeneous and the particular. So c1 e to the t plus c2 e to the negative t plus 18t minus 5. So that's the general solution for this particular differential equation. Now let's do one more. Let's do this one. And they want us to find, use under these initial conditions. So z double prime plus z The homogeneous solution, let's find it first. So the homogeneous solution is when the right side is 0. So our characteristic equation is r squared plus 1 equals 0. If we subtract 1 from both sides, take the square root of both sides, we get r is plus or minus I. So in complex notation, that's 0 plus or minus I. So that means our homogeneous solution does not have an e to the RT, because e to the RT, or in this case, AT, would just be 1. Remember, when we have a complex solution, it's e to the AT cosine BT, where B is the coefficient of the imaginary part. And then e to the AT sine BT. So A is the real coefficient, B is the imaginary coefficient. And we have a C1 here, a C2 there. Well, since e to the 0 is just 1, that makes our homogeneous solution C1 cosine t plus C2 sine t. That's our homogeneous solution. Now, if we want to get our particular solution, notice that our first thought for our particular solution is a e to the negative 7x. And look down here, I've been using t's. These are supposed to be x's. X, 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 and x, because in this problem, our independent variable is x instead of t. And notice that negative 7, r is not negative 7, so we don't have to pick up a t or a t squared in front of it. We don't have a double solution or a simple solution of negative 7 to the auxiliary equation. So our first derivative of our particular solution would be negative 7a e to the negative 7x, and our second derivative would be 49a e to the negative 7x. So if we substitute this in, and here I go getting my letters all confangled. I'm used to all the other problems, our variables being y and t. Here, our dependent variable is z, so this would be z of h instead of y of h. So our particular solution for z would be this. So we're going to substitute in place of z double prime, 49a e to the negative 7x, in place of z, a e to the negative 7x, and on the right side, that's equal to 5 e to the negative 7x. So if we combine like terms on the left, we have 49a plus 1a, so 50a e to the negative 7x, and on the right, 5e to the negative 7x. So this is the coefficient of e on the left. This is the coefficient of e on the right. So that means 50a and 5 must be equal. So if we solve for a, we get a is 1/10. So our particular solution is 1/10 e to the negative 7x. So that means our general solution will be our homogeneous plus our particular. So that's our general solution, but that does not give us our solution for the IVP. We have some initial conditions. that when x is 0, z is 0. And in the first derivative, when x is 0, z is 0. So we first derivative when x is 0, z is 0. So we need our first derivative, z prime. So the derivative of the first term, we would get minus c1 times sine x. For the second term, c2 cosine x. And for the last term, minus 7 over 10 e to the minus 7x. So for the function itself, if we plug a 0 in, we get c1 times cosine of 0 plus c2 times sine of 0 plus 1/10 e to the negative 7 times 0. Cosine of 0 is 1, so we get c1. Sine of 0 is 0, so that's gone. E to the 0 is 1, so that last term is 1/10. And what do we get when we plug a 0 into our function? We get 0. So this was plugging a 0 into our function. So if we solve that, we get c is negative 1/10. If we substitute a 0 into our first derivative, we also get 0. So our first derivative is 0 when we plug a 0 in. So we get in our first derivative negative c1 times sine of 0 plus c2 times cosine of 0 minus 7/10 times e to the negative 7 times 0. Sine of 0 is 0, so that term's gone. Cosine of 0 is 1, so that gives us c2. E to the 0 is 1, so that gives us minus 7 over 10. And then we said that when we plug 0 in to our first derivative, our answer is 0. So that makes c2 7 over 10. So finally, that makes our solution c1, which is negative 1/10, c1 times cosine x, our c2, which is 7/10 times sine x, and then plus 1/10 e to the negative 7x. So that's our solution given our initial values.